首先，让我们欢迎中央研究院院士李琳山先生所带来的迎向人工智慧的灿烂阳光。Ladies and gentlemen, please welcome Dr. Linsan Li from Academia Sinica.
Good evening. I'm sorry. Good afternoon, ladies and gentlemen. First, I have to apologize that all my slides are made in Chinese. And I was told that I can choose my language. Of course, I prefer to use Chinese. But then today I realized this is an English-speaking conference. So I'm slightly worried about what language should I say. So I try to speak in English more. However, sometimes I may switch from Chinese and English from time to time. So let me try and see if that works. So my pleasure to share with you today, my great pleasure here, and to share with you 迎向人工智慧的灿烂阳光. Let's welcome the sunshine of artificial intelligence. We all know there are many different explanations about artificial intelligence. I tried to find this from Wikipedia. They say there are many different explanations. For example, intelligence exhibited by machines is artificial intelligence. Also, any device that perceives its environment and takes actions to maximize its chance of success, that is. Or a machine that mimics cognition functions of humans associated with other humans, and so on. Well, that's not what I like to say, but with these definitions, what I'm going to say is that speech technology is a part of artificial intelligence. And let me start with speech technology. So what is speech? Well, speech is, the sound of our language. And they are waves in the air, and we use a microphone to collect them to make it into an electric signal. And then we try to change from every waveform into a sequence of points or real number to make it a real number sequence. And we use this real number sequence to do the processing. So what do I mean by speech technology? I mean, for every sentence, for example, here is a signal saying 今天的天气非常好. Here is a small segment of it, and that's a sequence of real numbers. But usually we don't rely only on signals, but instead we know that speech signals are structured. And there are quite complicated linguistic structures which we can learn from. So we can try to organize those linguistic knowledge in terms at least lexicon and grammar, such that the lexicon tells us that this sound followed by this sound is this word. And this is another word. And this word followed by this word is a phrase. And this is told by the grammar. In this way, the lexicon and grammar can be organized either by hand or learned from computers. And therefore, we can use both the signals here and the linguistic knowledge to try to do whatever we like to do. So this is a double-level signal processing. The first level is the signals. The second level is those linguistic knowledge behind the signal. So below, I like to try to tell a short story regarding how we started and how we come along. In the early years, 1980, that's the era, I call it the era of Chinese computer with large keyboard. What that means is, at that time, we already have the English typewriter for a long time. And we already have the early version of personal computers. However, if we like to produce a Chinese document, we need to have a very large Chinese typewriter with a very large keyboard. On it, there are thousands of Chinese characters, each with a button. So the typer has to find one character by one character and find the button to produce those characters. At that time, many people discussing, our Chinese characters so difficult? Is there any way we can do better, just like English? They have very small keyboard, only 26 characters on it. So many people think about, for example, radical systems, 字根法, or phonetical symbol sequence, 注音符号法, and so on. There's a time when I returned to Taiwan, when I was very young, and I was thinking that, can we enter the Chinese characters with sounds? The basic idea is that in our language, every character is pronounced as one syllable, and the total number of syllables is very limited, slightly more than 1,000. That's a small number. So can we do that? After study, I found it's very difficult, because that means we wish the computer to listen to Mandarin. That's difficult in 1980s, because at that time, this is not possible even for English. Not to mention, we have nothing here in Taiwan. So I thought, well, we should probably start with an easier inverse problem. That's to let computers speak Mandarin first. I think that is easy, because we just try to produce all the thousands, slightly more than 1,000 syllables, and then we should be able to put together them into every sentence. And I tried great effort to achieve that, and then put them together into sentence. Unfortunately, whenever I come up with a sentence, I listen to it, and I found that I cannot listen to it. I cannot understand it, and it is just totally wrong. I don't know why. 我百思不得其解. And very fortunately, I met a linguist at the time, and she told me that, oh, of course you're wrong, because in a sentence, every syllable, the pronunciation of it, or the prosody of it, 它的抑扬顿挫, is depending on the previous and following characters. 根据它的前后文会改变的. Well, then this is really difficult. Then I thought what we can do is to find some general rules from the data. And I think by 抑扬顿挫, the prosody, that means the pitch, the energy, the duration, and pauses. And so we made a lot of sentences and record the voice. And then we analyze by hand, see is there any general rules in it. But today, I just realized this is just data science, but in early years. At that time, all the data are made by human and analyzed by human, and only very tiny amount of data. Otherwise, this is just data science, 古代的数据科学. Eventually, after great effort, well, we come up with a system. When I enter the characters or phonetic symbols, we do heard the sound that we can understand, although they are not as good, but we can understand it. That's 1984, and I call it text-to-speech. Here I have a small voice that you can listen to it. That's recorded and converted to a digital version now. You can listen to it.
各位好，这是一套中文的文句翻语音系统。
And so on. Now, after this, the next question is, because we know at that time we understand the signals has to do with the structure of the sentence. Then I think we need to be able to analyze Chinese sentences. And that's difficult. So we made great effort to do it. For example, here a phrase, 被李四叫去吃饭的小孩. Well, that's very complicated. So we made great effort. At 1986, we were able to analyze it into a tree structure. Now we understand this is the early stage of natural language processing, 古代的自然语言处理. After that, I think we are ready to do the speech recognition. Now, I set up the goal to be for large vocabulary of unlimited sentences because it's for entering Chinese characters. But it's really difficult, so I think we can do is to just enter one character at every time because we are one syllable. We have one syllable per character. 我们的语言是一字一音呐啊，所以呢，我可以输入一个一个音来输入嘛。And another major reason is I understand that the pronunciation or the characteristic of every syllable is depending on the previous and following characters, as I just mentioned. And that make it difficult to recognize. So if I just enter every character one by one, then it will be isolated character, isolated syllable. That would be easier. Now, if I just enter one syllable, then I try to segment the problem into smaller problems to recognize the consonant, the vowel, and the tone. 我们的四声啦哈，声调。And even if we know the song, the syllable, you know there are many harmony characters sharing the same song. 很多同音字。And we need to know which character we are entering. So after great effort, we eventually were able to do this part. Then I just realized there was another major problem, that is how to put them together. Because at that time, the software are very weak. Everything had to be done with the help of hardware. So there are a lot of hardware there. So I think, well, probably we should try to integrate all this hardware together. Up to 1989, I really completed a hardware to put everything together. However, that hardware never worked. And then I start to think about doing chip because we were able to do chips. So up to 1992, we produced 2 chips, but that's still far from a machine. Fortunately, in 1990, we start to have paracomputers, at that time called transputer. So I use all my fund of my lab to buy a transputer. And that includes 10 CPUs and try to connect them together. And then I try to redo everything on the para software. At 1992, eventually we come up with the first successful recognition system. And here is the graph for a circuit for the hardware in 1989. This is a photo for the complete hardware. You can see very complete hardware there. As I mentioned, this never worked. Now, here is a chip we developed, and we didn't use it because it's far from the machine. Eventually, we come up with the first machine. I think that, well, that's really great. So I wish to give them name. The name is Golden Mandarin 1, 金声一号. The reason I choose this name because I try to find a classical words in the literature, 古典文献里边找一个典故 to describe the most beautiful song in the world, that is 金声玉振 or 金玉之声. And that's why I called it 金声一号 or Golden Mandarin 1. And this machine can only accept one syllable at a time, and very, very slow and very complicated. However, that's the first time we saw a recognition system which can recognize Chinese with unlimited sentences. Here is a video, also recorded at that time and converted to digital file now. And you may see this person is myself. I used to be young. 每一个老人都曾经年轻过。Let me listen to it very briefly.
这是一台国语听解机，它主要的功能是可以把由极大字汇组成的任意文句的国语，直接转换成相对应的中国字。在操作的时候，我们的声音由这个麦克风输入，首先通过放大跟滤波，然后进入个人电脑。 再由这个个人电脑把所有的资料送给全平行式的电脑，也就是 transputer system 来做所有的操作。底下来示范几个句子。以个好，停一下。
Okay, you see, it takes several seconds to recognize a syllable and so on. The major breakthrough after that will be Golden Mandarin 3 in 1995. At that time, we were able to recognize continuous speech without entering one by one. And in this way, the major problem you understand is that because, as we mentioned, the characteristics for the sound for every syllable is influenced depending on the previous and following word. And that's complicated. But at that time, we have the method to learn from data. Let the machine learn from data. And now we understand this is machine learning. This 古代的机器学习. And because of limited computation resource, we made two versions, PC version for short utterances entering, and workstation version for long sentences. And let me show you a PC version here.
这是一台以 PC486 为平台，加插一片 DSP 板子的国语听写机。它最大的特色是可以接受任意断词的延续短句。现在我们来展示其输入方式。电脑科技的进步。
I will show here. Takes some time. Okay, it is here. It's entered
改
there.
变了人类的。
Okay, that's a history part. Now, today, all of you know what is the most well-known speech technology will be the multilingual personal assistant with capability of speech technologies. And for example, the Siri of Apple, or Google Home, or Cortana of Microsoft. It can listen to and understand human speech. And also it can even answer questions. For example, who is the president of the United States and so on. How is this done? Well, they put everything on the cloud. You know, what cloud means is there are unlimited number of computers there with unlimited resource. And therefore, you can do everything in the cloud. So when you speak to your iPhone or whatever, then your voice is transmitted to the cloud and do speech recognition there to understand your questions. If it's needed to find the answer, they can do Google or search the Wikipedia or something and get an answer and make a sentence, then speech synthesis and come back, send the signal back. So the cell phone is just a voice interface, and everything is done in the cloud. If we look at the technology used there, we found that they almost use all the available advanced cutting-edge technologies. For example, the cloud, the big data, the deep learning, dialogue technologies, the Google, and so on. With the help of all these cutting-edge technologies, the performance of such system becomes acceptable to many users. And that's what they have today. However, all these systems needs to have speech recognition and speech synthesis. And all of them support Chinese. So if we look at the Chinese recognition and synthesis there, we found that all they did, in addition, except with cloud, with big data, with deep learning, and so on, what they did is the basic framework and the basic structure of their work is almost the same as what I did 30 years ago. In other words, even after 30 years, only the big company in the industry like Apple, Google, they can produce this kind of product first. But 30 years ago, we have very limited resources. We only have very tiny amount of data produced by ourselves, very tiny of data, and we use them to train very poor personal computers with very limited computation resources. And we wish to do this as they are doing here now. So all we can say that at that time, we are really have very good vision, and we are really very bravely fighting for our dreams. Now let me very briefly explain the process for speech recognition. Let me start with the isolated word recognition. For example, to recognize from 0 to 9, the 10 digits. We start with unknown signal. We try to extract features to construct vectors. And use these vectors to compare, do pattern matching with a set of models. If we are recognizing 0 to 9, every digit has a model. 1 has a model, 9 has a model, and so on. We compare with all the models. And these models have to be learned from training data. We have to tell them, this is 9, 9, 9, and so they learn the model of 9, and so on. Now, let me explain, what is the features? Well, by doing extracting features, that means we start with the signal. For example, we use a window to collect 512 real numbers. We try to convert them into a series of parameters, important parameters describing the sound, and put them as a vector. Then we slide the window here and do the second vector, then slide window again to do it here. So we get vectors 01, 02, 03, and so on. And what are these parameters? Well, up to now, it's about 39 parameters, and they describe the relative relations between our tongues, lips, teeth, and so on. Why? 当我说啊的时候，我说的啊跟你说的啊一定很不一样。可是呢，我说啊跟你说的啊很一样的地方在哪里？我们的口型、唇齿舌的关系是很像的。And that's the relation among the tongues, teeth, and tongues, which is invariant across different sounds, different speakers, and so on. And scientists found that this parameter actually simulate the frequency analysis of human ears. Well, what is that? You know, in our ears, there is this part, nair. There are some kind of pipe, and from the diameter from large to small, so it responds to different frequencies. 我们的听觉神经末梢长在这上面， so they can analyze different frequencies. And as a result, we know that we have this kind of parameters actually simulate human perception. Now, how about the models? The 模型, what are the models? Well, up to now, 最经典的, the most classical model, and even used today, is Hidemaru model. The Golden Mandarin 1 we mentioned in 1992 used this model. And today, Microsoft announced that their speech recognition has a performance the same as human. They still use this model. So what is this? Well, if you're producing a model for 0, that means the signal is changing from Z to 0, right? So so it's a sequence of states. The first state describes Z, then probably E, so we have Z and Rho, and so on. So different states describe different signal characters. So when we have the signal represent a sequence of vectors, as we just mentioned, some vectors belong to this state, some vectors belong to this state, and so on. Now the problem is, we never know which stage should be longer or shorter, because you can say 0, you can say 0. So how can we do this? Well, we just modeled it by the so-called state transition probabilities. For example, if this probability, this is the states 1 to here, if this is 0.1, it's 0.9, that means if the first vector belongs to 1, probably the next one will be 2, because the 90% of probability, it will goes to 2. But if this is 0.9 and this 0.1, then if the first one is belong to 1, then probably the next several still 1, because there are 90% of probability that it will return to itself, and so on. So these probabilities describe how every state should take longer or shorter period. And they can be trained, and they can be learned from data. That is machine learning today. Now, another problem is, even we know this vector belongs to this state, well, they all look different. How can we do? We use a probability distribution to describe it. So it can be of any type, but with different probabilities. So what is the difference between the different states? They just have different probability distributions. And these probability distributions can be learned from data. Again, machine learning. And what can we do is to use a series of Gaussian.高斯分布是最基本的几率模型. So we use a series Gaussian to approximate any distributions. Of course, here I only draw one-dimension distribution. Actually, there are 39 dimensions, as I just mentioned. Now, I just mentioned is isolated word recognition. But how about continuous speech? Well, for continuous speech, we have to worry about, for example, we just mentioned lexicon, 词典, and 文法, grammar, and so on. As we just mentioned, when we heard this sentence, 今天天气非常好, how do we know this is this 金 rather than 黄金的金? How do we know this is 天 rather than 天饭的天? There are many harmonic characters sharing the same syllable. But we know it is this because in our mind, we also have, in our brain, we also have some kind of lexicon and grammar. So we just realize what these characters are. And we should do this. How can this be done? Well, we start with, for example, this is the input signal is English. This is speech. Now we first transform it into a sequence of vectors, as we just mentioned. And then we try to find all the basic units in English, like this. For example, this word is represented as this series of units, and this word by this series unit, and so on. We use all these basic units to construct models for them. That's what we call acoustic models. And then we use a lexicon, 词典, tell us how many words are possible. And for example, this sequence of units is this word. This sequence of units is this word, and so on. Does this solve the problem? No. Why? We still need what we call language model. Why? Because these sounds are actually very similar to each other. And this also. Even human ear may not be able to recognize them very correctly. So for the machine, they only give us a set of possible sounds with different scores. So what can we do? Well, they are searched through the lexicon, become many different words. Let me give you an example in Chinese. This is a sentence. The correct answer is 好语不断，台东两人失踪. However, because many sounds are very similar, so 好语 may be very close to 陶艺, 不断 may be close to 无端, 台东 may be close to 台中, 两人 may be 两人, and so on. So you may got a sentence like 陶艺无端，台中两人失踪. The correct answer is this. But can the machine know which one is better? Well, you can easily see this sentence is 奇奇怪怪，不对嘛。Why? Because you never saw this kind of sentence. But this is reasonable because this can be easily find similar sentence in database. And that's why we use this 语言模型 language model. We can collect huge text database and try to collect the computed probability of this word in the beginning of the sentence and the probability that this word follow this word and this word follow these two words and so on. These probabilities are the so-called 语言模型 language model. So with all this input, now what is this part? Linguistic coding, 语言解码. It takes a lot input, including the vectors from the sound, all the Kuss models, or the lexicon and language model to find the correct sentence. How can this be done? Well, we start with a lexicon tree, 词典树. We put all these words together into a tree structure. Suppose we have 60,000 words, 6万个词, they are constructed into one tree, 词典树. For example, this word speak is this sound followed by this one, followed by this one, followed by this one. If we change this one to this one, then this will be speech, and so on. So every word, every leaf of the tree is a word, and every arc here is a model or a sound. So in this way, we can, for every entered signal, we can search along the path of the tree to give scores, and then to find the possible word for every possible segment of sounds. And in this way, we don't have to repeat the computation because they are just searched one by one. Of course, at the end of every word, you need to connect to another tree because another word will follow this word. So what you'll see is something like this. 这是一棵树，它有6万个词的话，有6万片叶子，每一片叶子后面接下一棵树，所以呢，这个词典树很容易就展开成一片原始森林。Then you have to search across the forest to find the path which correspond to the best sequence of words. That is your answer. Now you know this is a very standard problem and solution for 人工智慧, for artificial intelligence, that is tree search. Now, with the deep learning today, what has been changed? Well, the model we just mentioned, still there, the Hidemaru model, the sequence of states. Now I plot them vertically before I plot them horizontally. But this is same states of models. The only difference is now we can evaluate all these probabilities using deep neural networks rather than using a series of Gaussian probabilities. But these Gaussian probabilities are still very useful because even this deep neural net need to learn from data, and the data has to be segmented by models. They are composed of Gaussians. Of course, today there are more advanced technologies. For example, there are a lot of people saying about end-to-end deep learning for speech recognition. Here is just one example. There are many different architectures. Here is one. For those of you may be very familiar with this, this is bidirectional LSTM, several layers, and this is attention. And then this is input sound, and this is output words, and so on. In this way, we may leave alone. We can give up those Hidemaru models, and we can learn from the sound to the lexicon to the sentence structure all together. This is deep learning. This is achievable, however, today only realized by some groups in some experiments, not all. And you may say that, well, is this speech recognition just useful for Siri of Google, of Apple or Google Home? Of course not. There are many different possible applications in the future. I usually like to say this example, that is, I usually call voice version of Google. We know that Google is able to find every article in the world because they have seen all the articles and then developed the indexing. Of course, today, the machine can listen to all the sounds, for example, all the sounds in YouTube, all the sounds in all the online courses, and so on. In that case, of course, machine can also develop the indexing for them, so we can have voice version of Google. Actually, this is not new. We actually have the voice version of Google for 公视新闻, public TV news, as early as 13 years ago. And you may listen to this very brief demo here. You understand what it is.
王建民读的国小。
王建民读的国小。
王建民来了，回到民国81年毕业的台南市崇学国小。
So understand, that means the machine actually can find every utterance without human labeling. Now, next, I like to spend a few minutes to explain why Chinese is different in speech recognition from Western languages. And because we have very spatial linguistic structures. For example, 我们是方块字, we are not alphabetic languages. Every character has its meaning. However, we make sentence by words, 用词造句. Every word has its meaning, relate to the characters or irrelevant to the characters. 书店就是卖书的店，但是风流不是风吹的流。So there are very complete relations between characters and words. 字跟词之间关系是非常复杂的。And also in our sentences, the word boundary is not clear. 电脑是一个词，科技是一个词，的是一个词，科技的是一个词，电脑科技是一个词，电脑科技的是一个词 and so on. The words are very complicated and the words are not well defined. Actually, we can put together short words to make a very long words. We can make long words abbreviated as short words. A word can be segmented and put something in between. For example, 洗了一个大澡，澡不是一个东西哦，可是我们可以洗它的。Also, new words are generated every day. For example, 小确幸 or 飞鹤家园 and so on. As a result, there are almost unlimited number of words. 词汇无限大。It's impossible to have a lexicon. 你要想有一个词典包含所有的词，其实是做不到的。我们刚才讲那个西方语言那个技术里面，它就是要一个词典呐。我没有一个词典怎么办呢？我词典里面一大堆的词都不在词典里面怎么办呢 ？Secondly, 我们是一字一音呐。Every character is pronounced as a monosyllable, but there's only limited number of syllable, 1000多个音。So every syllable is shared by many characters, 很多同音字。And we have tones, 我们有声调。And different tones gives different characters a different meaning. For example, here, 一 and 诗, the two sounds with different tone will give many different words. For example, 一时, 一世, 一诗, 一史, 一世, 一时. There are many of them. And also, many words actually pronounced the same, pronounced exactly the same, but with different words. For example, you never know that 香蕉 actually can be eaten as 香蕉. When you wrote computer programs, 程式, you also live there, and so on. In other words, we have only limited number of syllables, 很少数有限的音, but carrying plenty of linguistic information. So this level of unit, 音, does not exist in English or other Western languages. Next, in our language, the order of words are very freed. For example, when you are like to say this concept that I like to depart tomorrow morning at 6:30. Do you know there are how many ways to pronounce this sentence? Well, at least this. You can say 明天早上6点半 and so on, or 我明天要早上6点半 or 明天早上我要 and so on. Many different. So, what can we do? In early years, this is a very difficult problem for us. But today, many of you who know deep learning, machine learning very well, you may say that, well, we think this can be learned from data. Yes, you are correct. Today, with very strong computers and with big data, it's possible to learn from data by machine without trying to analyze all these difficult problems. So I would like to say that 由古代到今天, from early years to today, the difference is that in early years, the machine is very weak. Data is very limited. At that time, the artificial intelligence is very limited. 人工智慧非常的单薄. So we have to use human knowledge to find the problem and find a solution and try to embed this human knowledge into very weak artificial intelligence. 把人的智慧注入非常单薄的人工智慧之中. But later on, when we have strong and stronger machine and much more data, then more and more problem can be solved. The answer can be found by machine learning from data. And then, what are the human knowledge to do? Well, the human knowledge is try to guide the machine to find the solution. Because it's always better to learn from huge quantity of data than with machine, than human being themselves. For example, 我们举例来讲，一个人一生从生下来到50岁，他听过多少万小时的声音 ？Well, the machine can learn those 多少万小时声音是没有疑问的。The machine can even learn thousands of people's, learn the sound heard from thousands of people. Of course, the machine may be able to analyze the problem better than human knowledge. And this is what we have today. Now I'd like to mention something about artificial intelligence in Taiwan. We know artificial intelligence has been existing for many years in the world. I believe it also has been existing many years in Taiwan, but I don't know exactly where they are and where they started. However, I do know about computer science department of Taiwan University. And this is the old building of that department in 1980s. I was department head there, so I know that. And I tried to find the document there made in 1985. 这是85年的系务会议的记录. This is made by Chinese typewriter, 中文打字机打的文件. It's a table of projects at that time. You may notice that, well, here a series of projects under the same title, Artificial Intelligence and Applications. There are so many projects there, 10 of them. So as early as 1985, we do have a group project including 10 sub-projects in Taiwan University. And if you look at here, they are supported by National Science Council, 国科会, which is 科技部的前身. And they do support with a lot of funding. So we know that National Science Council or 科技部的前身 really have very good vision more than 30 years ago. They are not starting now. They did it very early. At that time, I remember at that time I did plot a figure of this project, but I am not able to find it. And I try to redo it now. So this is done by computer today. And for these 10 projects, there are a set of projects working on basic systems, a sixth problem working on programming languages. With this together, we are able to do a lot of applications. And this is the group project of artificial intelligence at that time. At that time, we also made great effort to promote this effort on research of artificial intelligence. So we have a series of lectures, demos, programs, activities. We invited visitors from foreign countries, including Professor John Mccarthy from Stanford. 有照片为证. And this is in front of our old building. And you know, this young person is myself. More important, this Professor John Mccarthy was known, and even now was known as one of the founder of artificial intelligence. He fly all the way from the United States to come to Taiwan 来为我们站台. And here you may see a few faces. They are very important people who support and work on this project. For example, here is Professor Lin Fengqing. Here is Professor Lin Yipeng. And here is Professor Xu Qingqi. They are the major supporter of this project. And we have a total of 10 projects. And they are actually the next 3 department heads after me. And actually, we also have attended a 国际电脑围棋大赛哦 International Go Grand Challenge in 1985. 我们南瓜冠军跟亚军 we got championship and the second place. 轰动 and 有照片为证. And this is a photo, and you'll see that the leader of these 2 groups to get championship and second place is here, our Professor Xu Shunqing. And actually, Professor Xu Shunqing said that he used to be in Department of EE. And then some people say he's not working hard because he always play Go. So, but then he found that in our computer science department, playing Go is artificial intelligence and even academic research. So he is very happy to come to computer science department. And that's why we started the research on Go that early years of 1980s. Now I'd like to mention about AlphaGo. We all know that AlphaGo, a few months ago, fight with the Go master, 世界棋王, 大陆的柯洁. This is a photo when the game starts, and this is when the Go finished. And also, a group of 5 masters, 5大棋王联手 to fight with AlphaGo. And this is how they start, and this is how they finish. I'm not saying this. What I like to say is AlphaGo really 源远流长. Well, my English really is difficult. It's not able to say what is 源远流长. But what I mean is that, well, really the beginning is very, very early in a very, very far source. What I'm going to say is that, you know, this AlphaGo, there is a key person behind AlphaGo. That is Dr. Huang Shijie from Taiwan. He received his PhD in Taiwan. You may find out what is his PhD thesis title is written here. You may find here there are computer game, there are Monte Carlo, there are tree search, and heuristics. You understand, this is the 前世在前世的 AlphaGo 的前世的前世 or the previous generation of the previous generation of AlphaGo. And if you find out, well, who is the advisor of this PhD thesis? Well, we found that's 台师大林顺喜教授. And Professor Lin Shunxi 教授 actually did his master and PhD in National Taiwan University in 1985 and 1980. At that time, his thesis advisor is Lin Fengqing 教授. But his PhD and master thesis look different from, have nothing to do with 围棋. However, if you look at the year 1985 and 1990, that's the 80s. At that time, 围棋大赛轰轰烈烈。The 人工智慧计划风起云涌 in computer science of Taiwan University. So it's reasonable to guess that Professor Lin Shunxi, at that time, sometimes he may 茶余饭后会不务正业去玩围棋 use some spare time to play Go at that time. And then that incubate his interest and capability in advise the PhD thesis of Go playing. And that's why I say that AlphaGo 源远流长. If we think about AlphaGo 真正的最原始的源头在哪里？它真正种下种子的地方在哪里？我相信很合理的说，是我们台湾这是台湾种下的种子。那如果我们再回想 we look back the project of artificial intelligence in 1985, what does that achieve? Well, at least here is my project on Mandarin speech. At that time, I only start with 母音子音, and here's a project on 下棋, and we start with 象棋 and so on. But these projects are important. Okay, let's say again, 由古代到今天. As we said, in early years, machine learning and artificial intelligence is weak, and then it's getting stronger and stronger. We also see that today, they are very convenient or very strong product level technology. I say product level, that means those like Google Home, those like AlphaGo, those like Siri Google, Apple Siri, and so on. Well, they are developed with the resource of industry. Industry has a very fertilized environment, 非常肥沃的土壤来造就这些产品级的技术。On the other hand, even in those very fertilized environment, some seed are very important. 创造性的有竞争力的种子是非常重要的。So the industry and the academia should work together, 在各自的岗位上共同开拓共同的天地。Now let me very briefly look forward about artificial intelligence. I would say, in my view, I can hardly find any area, any domain which we will not use artificial intelligence. You may say, well, today there are many domains, many areas, they are not using artificial intelligence. I think because they do not know how to use it yet. That means there are still plenty of space, 有非常辽阔的开发的空间。On the same time, I cannot think of after how many years it will become useless. Probably in the foreseeable future, they can be used. And that means artificial intelligence is 可大可久, can be very huge, can be very long. So I would say the next few slides were difficult to translate into English. So let me say in Chinese first. 人工智慧不但是博大精深 very huge and very deep, 而且是海阔天空 much wider than the ocean or the sky. 不但是包罗万象 includes almost everything in our daily life. 而且兼容并蓄 can absorb almost all areas. 从天文到地理，从科学到人文，都可以被吸纳进入人工智慧之中。人工智慧不但是无远弗届 can reach everywhere in the universe. 而且是无所不在 is everywhere around us. 不但是变化万千 it changes unpredictable. You see here, these are the graphs produced by deep learning. 而且是一日千里 it changes, advances so fast. We know that when computers are so big and so dumb, there already exists artificial intelligence. After years and years, computer becomes so small. And when, in the beginning, the deep neural net has several layers. In a few years, it reaches hundreds of years. So it's advancing so fast. So today, when we saw the artificial intelligence, if we consider artificial intelligence as a human, as a life of human, then how is it today? I guess it's just a newborn baby, 出生的婴儿. Probably no, it is still in 腹中的妈妈肚子里. We only saw it. We only see it from the ultrasonic image. Or in other words, today we only see the first sunshine in the early morning. 曙光出现而已. But when we saw this 曙光出现, we know the sun is rising. So we know the next will be 天将破晓. The sun is rising and 天光渐亮. The sun was rising and rising. So the artificial intelligence today is a rising sun. It shines the whole world, and also it announces the rising of the sun. And the rising sun cannot stop it, cannot change it, and we cannot hide it. All we have to do is to face, to welcome the sunshine. And that's the only way 精益求精，可大可久. That's the only way to become larger and stronger and better. So we expect in the future to see 阳光灿烂，晴空万里. Let me end here to 以此与各位互相勉励. Let's work together. Thank you very much.
谢谢李林山院士。Thank you, Dr. Lin San Li.
Ladies and gentlemen, please allow us 60 seconds to change over the laptops for Dr. Shu's talk coming up next.
Okay. 谢谢李教授的精彩演讲。接下来，徐宏明教授的演讲将于1分钟后开始。